In the next episode of StarTalk, it's a Cosmic Queries All Chemicals edition. My co-host, Matt Kirshen, together we meet and greet Kate the Chemist. This is Kate Biberdorf from the University of Texas at Austin, and she tells us all kinds of things in response to our Patreon questions. For example, what is the only F word she does not allow in her classroom? That's kind of interesting. And can we use the gaseous constituents of farts to decide whether life exists on another planet? That's kind of freaky, weird there. And did you know you can take an inert element and make a molecule out of it? I didn't. I learned in this episode. So stay with us. Check it out. This is StarTalk, Cosmic Queries. This is a special chemicals edition because some of my best friends are made of chemicals. Of course, all of my best friends are made of chemicals. I got with me my co-host, Matt Kirshen. Matt, how you doing, man?
I'm good. I've just found out I'm made of chemicals. That's a little bit worrying, but
yeah, sorry. I meant to warn you in advance that I would announce
aren't chemicals dangerous? What? Yeah. Do we need to? Does there need to be a warning? Does there need to be yellow tape around me? What's going on? What do we got? Hopefully we'll find out.
So I know a little bit of chemistry because we need it in astrophysics, but not enough to be the source for this show. We combed the landscape and we rediscovered Kate Biberdorf. Kate, welcome back to StarTalk.
Thank you so much for having me. I'm so excited to be back.
Yeah, Kate, your moniker, your online moniker is Kate the Chemist, and
yes.
I love it. You have a PhD in chemistry, and you're now associate professor of instruction and of chemistry at the University of Texas at Austin. So that's just the kind of expertise we need when we comb our Patreon members who get exclusive access to the questions on our Cosmic Queries. So Matt, you've collected them. I haven't seen them. I don't think, Kate, you've seen these questions either. Only Matt has seen these questions. So
there are a lot of very good questions. I'm gonna try and get through them all. I apologize to any patrons we don't get through, but because there's a lot of good ones. So let's kick off with Soren Sarkar asks, at what point after the Big Bang can we say chemistry came into existence from the physics of the early universe?
Whoa.
That's heavy.
Yeah, sorry to drop that one right on you at the beginning.
Damn.
Yeah.
Tell us when your entire field of study started.
Of an atom?
Well, let me tee up Kate here. So Kate, like, early universe is really, 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 really hot. And as we expand, it slowly cools. So, as I remember, high temperatures are not good for making molecules. So what are some molecules that you might make first in the highest of temperatures as the universe cools?
Well, in the very beginning, we really only had two elements. I mean, we think that we only had the two of hydrogen and helium. And that was the very beginning. And the two of those reacted together. They kind of existed together for quite a period of time. And after some time, when the universe started cooling down, that's when we were able to actually start the molecules, just like you were saying. Because chemistry and the formation of molecules is all about exchanging electrons. And so nuclear chemistry, which is what happens a lot in space, that's about the core, the nucleus. But chemistry here on Earth is all about electrons. And so in order to form a bond between two atoms, we need to have some kind of electron exchange. So they're either going to transfer electrons or they're going to share their electrons. And unfortunately, when the temperatures are really, really hot, these atoms can't even hold on to their electrons. So in the very beginning, we didn't really have hydrogen and helium atoms. We had the nucleus. And so we had a species with one proton or a species with two protons. And so once the universe finally cools down, that's when we can start actually forming these bonds between each other, because the atoms can now hang on to their electrons. So a classic molecule that there was like a big hoodoo about it a couple of years ago, was the helium hydrogen molecule that was formed. So HEH+.
What?
Yeah.
What? No, that's not allowed. No.
What do you mean that's not allowed?
No. No.
I was like,
doesn't
that's
have
right,
my
isn't it?
permission.
Okay.
Helium does not have my permission.
If there's one thing I know about helium, Well, it's the squeaky voice thing, but if there's two things I know, it doesn't form any bonds with anything. So what do you have to do to make helium?
What magic are you, what sorcery are you committing in the early universe to make this happen?
Well, we have to have high temperatures. That's a big piece. And so we have to have enough. And there's also a velocity component. Those are the two main pieces. So these two protons or these two species have to slam into each other with enough velocity and high enough temperatures in order to basically have that strong force engage.
Fusion. Oh, okay. Got it. All in. All in. I thought they were somehow the helium atom, like full up with its electrons, was somehow mating with a hydrogen atom to make a HEH molecule. Okay.
No.
Oh, man. I was sweating there for a minute. Okay.
No. But it's just, usually in space, we don't find very many molecules because it's very difficult. The temperatures are unique, the conditions are really unique. And so oftentimes we find species without their electrons on them. So we're not finding full atoms, we're finding these charged ions. And so in order to have the molecule, you really need to have that atom component so that we can have that electron exchange. It's fascinating stuff. It's wacky stuff because here on Earth, that just doesn't happen like easily. But
we don't get the nuclear stuff. Yeah, the nuclear
exactly.
things.
Yeah, we don't have nuclear chemistry. It's so we have just regular old chemistry here on Earth.
Well, there's a follow-up question from Soren that I think is related to this. That is it possible for the periodic table of elements to be different in another part of the universe with vastly different conditions, or do we need another universe with different fundamental laws for that to happen?
Ooh, I love that question.
I do too. So let me give my answer, and then Neil, I want to hear your answer to that, if that's okay.
Sure.
Because my answer would be no. In this universe, we all have the same building blocks. We all started with the hydrogen and the helium components. And so we are going to then form the exact same elements with these same building blocks when we change the number of neutrons or protons or electrons that a sample has. So here in our universe, I personally think our periodic table is locked in with these elements. We can discover new ones still, but I don't think we're going to have completely different conditions.
Yeah, I agree entirely.
Do you agree?
Yeah, we look at spectra of stars, galaxies across the universe, and the spectrum matches what we can produce in the laboratory for the various chemical elements. So you look at like what carbon looks like sort of when you burn it in a lab, and it has a signature in the spectrum, and you find that same signature as you look out into the universe. So all these same elements are there. So we have no reason to think that the periodic chart would look different at all. And Kate, plus the chart is full, right? I mean, there's no room left.
Well, I'd fight you on that.
Oh.
Professor
Nerd fight.
Oganessian.
Let's go.
Yeah, let's go. So Professor Oganessian over in California would absolutely fight you on this. And so he has been responsible for the last 6 or 7 elements that have been discovered. He has this fascinating technology.
Oh, the heavy. Wait. I get you. Okay. So we're adding at the extreme end, but we're not crowbarring other elements in.
No.
That's all I meant. That's all I meant.
Yeah, I agree with you that the first 118 are locked in, but after that, we're still forming new ones. I mean, we could even go to another row on the periodic table. I don't know that I will ever see that personally. I'm optimistic that we will, but I don't know. Maybe my great grandchildren would see something like that.
And are you just showing off? Why does your chart behind you, for those who see this in video, say periodic chart of the atoms, where everybody else just says periodic chart of the elements? So do you know something that we don't know?
No, this is just an old one. Let me see what's the date. 1924.
Oh,
so this came from 1924.
Interesting. Very old. Okay.
Well, did they have all the information then, or is there a kind of here be dragons area?
It's wacky. When I first got this periodic table, my husband and I stared at it for 30 minutes. It was like the best date we've ever had because we're both chemists and we're looking at it. It was a nerd date. It was so cool because the way they talk about where the electrons are in the shells, it's just a different way of organizing the information. And so here, all of it is put into the elements little box, whereas on our periodic table, now it's organized in that very specific structure. So you have the 2 on top, and then it kind of looks like that bowl. Right? And so mine doesn't look like that anymore because we don't organize them that way.
Plus 1924, we were in the middle of discovering quantum physics, right? This decade is the centennial anniversary decade of quantum physics, which gave a full understanding of what the hell's going on the periodic table. So I love classic old stuff. Thanks for sharing that information with us.
Of course.
I think this segues quite neatly into the question from Scott Bringlow, aka Scott the Pilot, who has two granddaughters who are curious and science curious granddaughters, young kids. Firstly says, can you say hi to Beatrice and Louisa?
Hi, Beatrice. Hi, Louisa.
Okay.
And Scott's very grateful to have a growing community of female role models in science, and also asks, Scott was wondering about combining atoms under normal earthly conditions, and then about where in the universe atoms combine because of extreme conditions of temperature or pressure, perhaps. Where do we find strange compounds that would not exist on Earth? So you've already discussed this a bit with hydrogen and helium combining.
Well, but that would be a nuclear fusion. But I got a good one for you. Okay. So Kate, we learned in chemistry class that hydrogen is sometimes a metal, right? Like it's on both sides of the periodic table, which was kind of freaky to me. Mm-hmm. And I didn't fully understand that until I took astrophysics. So do they teach how it is that hydrogen can become a metal in the class? Do you teach it in your classes?
Not in general chemistry. No,
Right.
That's a little advanced.
Right, that's what I'm saying. It wasn't really there.
Yeah, not in your basic classes. You really learn more about that when you go into the lab. So my first introduction to it was when I used lithium aluminum hydride, and my graduate student was like, okay, this could kill you, so let's have a conversation about it. And it's like, okay.
Half the stuff on that table can kill you.
Yeah, exactly. Half the stuff on the table could kill you. But usually it has to do with the charge on the atom. So when hydrogen is negatively charged, it can behave more like a metal. Whereas when hydrogen is positively charged, it operates more like the gas itself. And we have the cool properties that you probably are familiar with because it's similar to what would happen out in the universe and space.
Right. So in the core of Jupiter, under very, very high pressure, Jupiter is mostly hydrogen and helium. Okay. It's gaseous. It's damn near like a star in its composition. And the helium, the hydrogen in the core under very extreme pressures creates the metallic properties of the hydrogen. And those metallic properties then enable dynamos to form, which creates a very strong magnetic field. So Earth has a magnetic field because we have an iron core, and that itself is magnetic. But Jupiter has a magnetic core because of what it's done to hydrogen. And that's when I first saw hydrogen, or knew of a place where hydrogen behaved this way under natural causes.
Oh, that's right. So that kind of relates. Joey Santos asks, I'm just going to combine this. Are there any theorized molecules that are only made possible to exist outside of the bonds of this planet due to cosmic phenomena or some sort that we can't recreate? And I'm wondering, actually, because that second part of the question, it sounds like it might not happen naturally, but some of these things can be recreated under extreme lab conditions.
Yeah, once you know how you can create it. I got one in the universe, but Kate, do you have any? Were there any that eluded us until our lab experiments got better? Know of?
Oh, absolutely. So like xenon, we thought xenon was an inert gas forever. It is in the periodic table. It's a couple below helium. So we would expect for it to be inert. But once we got into the lab, we were actually able to make XeF4, so put 4 fluorines on it. And that was shocking. People were not expecting that at all because you thought it was an inert gas. But it turns out it's only inert under certain conditions. What's the one in the universe you have?
Wait. So that reminds me, Kate. So the properties that we list for your 118 elements, we all have to agree under what condition those properties are being reported, right? So if we say it's liquid, well, it's only liquid in a certain temperature range. So It's not natively liquid. It just happens to be liquid because we're measuring it in our own labs at 72 degrees, right? Mm-hmm. So how do you distinguish between...
So 25 Celsius. I got to throw that in there.
No, excuse me. Okay. 25 Celsius. Excuse me. So...
Well, you use Fahrenheit. That's like the only F word I don't allow in my classroom. Like, I'll take everything else.
So someone could say Celsius, and that's just fine. But
I'm fine with that. I don't care.
That's funny.
Because they're more of a Kelvin fan? What are we doing here? Can I ask, because
wait, I'm not done. Wait, hold on.
Sorry, okay.
Hold on. Okay, so I guess what I'm saying is on the chart where you have room temperature at 25 degrees Celsius, that to say something is a liquid reported as a property of the element, it kind of doesn't make sense to report properties of elements unless you have a full discussion under what conditions you are measuring those properties. Isn't that right?
Yeah, that's an excellent point. And so we always talk about STP, so standard temperature and pressure. And so in general, if we don't say otherwise, it is safe to assume we are under the conditions of 25 degrees Celsius, which is like loosely room temperature, and then a pressure of 1 atmosphere, which is again loosely the pressure on Earth. And so in my class, I say this all the time, like we are only studying the things on Earth. So that's why we use these conditions. And then when we move to astrochemistry, that's when we take ourselves off of Earth and move into the universe, where it's more nuclear chemistry, whereas on Earth, it's more chemistry, like traditional chemistry.
All right. And so, and one more thing, Matt, and then I'll hand it back. You can have the speaker's mallet or whatever. What do they pass around in the
Microphone?
Okay, the early version of the microphone was a speaker stone or something. You couldn't speak unless you had the speaker stick.
Oh, yeah.
So a friend of mine from the UK noted for me that there's an element that is solid in the UK but liquid in the United States.
Gallium?
Maybe it was gallium, because in the UK, their room temperature was colder than in the United States by a few degrees.
I bet it was gallium.
So what's the melting point of gallium?
It's 30 degrees Celsius, so just a little bit warmer than room temperature.
Okay.
So, which is 85 degrees Fahrenheit for the Americans.
Yeah, we can totally, there's plenty of places that are 85 here in the United States.
That actually was throwing me, because I seem to remember from school chemistry that 20 degrees Celsius was room temperature.
That's 68 degrees Fahrenheit. No one would call that room temperature.
So hang on, remembering from school chemistry, I thought all the noble gases were inert because they've got full electron shells. So how do you get 4 fluorine atoms onto one?
First of all, fantastic job on that. That is amazing that you remember that they have full electron shells, and that's why they're not reactive. So they're not hunting for another electron. I'm very impressed.
A-level
by that.
chemistry from 20 years ago, still hanging on in there.
Great job. Your high school teacher would be so proud, or whoever teaches A-levels at that. But the answer is extreme conditions. Like that's always the answer when you make something work that you're not expecting to. It's extreme conditions. And usually for us, we can alter pressure, volume, and temperature. And so if we do something at a low volume, then it's going to force these atoms to interact. And so for chemistry, it's all about collisions. Did they collide, and did they have the proper orientation? So for example, if I have one thing that's horizontal and another thing that's vertical and they slam into each other, it might not be a favorable interaction. But if they now move around the flask a little bit more and now they're both horizontal and they slam into each other, now they can actually form that molecule. So it has to do with how they collide and in what orientation.
Man, it's more complicated than I ever thought.
It's very complicated, yeah, because you don't necessarily have a reaction just because the molecules collide. You have to have the proper conditions. And high pressure really helps that because it's forcing those collisions to occur. It's forcing those atoms or molecules, depending on what you're studying, to actually go through those collisions, breaking bonds, forming new bonds, and you just need to have those collisions in the right orientation.
Wow. All right, we got to take a quick break, but when we come back, more with Kate the Chemist in Cosmic Queries, the Chemicals edition. We'll be right back. We're back. StarTalk Cosmic Queries, Chemicals edition with Kate the Chemist. All right, we got Matt Kirshen with us, reading us the questions. So Matt, give it to me.
Don Lane from Michigan says, I recently read an article about how the asteroid, is it pronounced Ryugu? Ryugu, was full of organic molecules. What does that mean for possible life in the galaxy?
Yeah, I mean, when we looked out in the universe wondering whether life was rare, and then we find the building blocks of life everywhere. So Kate, how important do you think let me say that differently. If these asteroids and comets hit Earth, delivering these basic ingredients, what more do you need to give us life?
I mean, that's a basic part of it, right? Is you need the main things that our bodies are comprised of. So you need the carbons, you need your hydrogens. In our personal human body, we also need oxygen. That's the number one thing we need. And so we were able to sustain life here on Earth because of its atmosphere. I mean, it is 21% oxygen. Even though it's primarily nitrogen, that oxygen on Earth is what we need to sustain life. So if we were to have life over on other planets, somewhere else in the universe, depending on what I'm just going to say human, but whatever their body is, whatever their species is, they are going to have something else that they need in order to breathe and function. And so maybe it's not oxygen, maybe it's nitrogen, because their system operates a little bit differently.
Okay, so but you're saying it's necessary to have these ingredients, but maybe it's not sufficient. We need some other things going on. In other words, if you just have a tide pool with all the right ingredients, will some creature crawl out given enough time? Or do we not know enough about that transition to say at this point?
I do not think we know enough about that transition, but I do think that when we have atoms around each other under the right conditions, like the extreme conditions, a lot of things can happen. I mean, we're very far away from doing crazy nuclear chemistry here on Earth, but we can see out in the universe that when you're at high temperature and when you have high velocity, really fascinating molecules can form. So it really just depends on the conditions and, how close that particular planet is to their sun. Are they really close? Is it very hot? Because you're going to have different reactivity than if we're at something like Pluto, which is really, really, really far away from the sun. Completely different chemistry.
That also kind of connects to listener Kenneth from Atlanta, who says we talk about the Goldilocks zone, the importance of liquid water and other chemicals in the periodic table that could be analogs to the biochemistry on Earth. But are there any models that investigate biochemistry based on completely different temperature scales and different phases of matter? So I think that relates to what you were talking about with these different conditions on these different parts of the...
Yeah. Kate, what is STP on another planet? Do you guys think about life under those very different conditions? Maybe not liquid water, but liquid.
Kenneth says exactly that. He says, what might there be different chemicals in liquid form that could serve as a metabolite on different, and what gases could be breathed?
Right. My favorite. I saw a comic from the New Yorker where there's aliens that just crash landed in the desert, and they're pulling themselves along the desert floor, and they're saying ammonia.
Yeah.
So can you imagine that, Kate?
Yes, I can. I can see a system based off of nitrogen. So our system here on Earth is typically pretty heavy in carbon, hydrogen, and oxygen. Like those are our big pieces. And so something that is just a neighbor of that is nitrogen. And so it would not be that unusual for me to see, or to believe that we could have other life forms that are dependent on nitrogen. So maybe they breathe nitrogen gas. Maybe they need to drink ammonia because that's what works in their system. But for us,
ammonia
because
is the chemical symbol for ammonia?
NH3.
NH3. So that's your nitrogen showing up there again.
That's your nitrogen. Exactly.
Right.
Yeah. But I think a huge part of it, just to go back to what you said about STP, is here on Earth is we do have an atmosphere. And so we do have all these gases that are pushing down on us, and we have chemical reactions based on that. But in other planets, they don't have the atmosphere, so they don't even have that pressure. So what what that life form would be breathing in or not, that's what's weird for me. I have a hard time with that piece because, how would that work if there's no atmosphere? So for me, I personally believe that if there is life in other places, there's got to be an atmosphere in order for those natural chemical reactions to occur. What do you think?
All right. Yeah, I think it can happen underground, right? I mean, you can have pressures underground where you don't have to worry about what's above ground. In fact, I just recently learn this, Kate, you're closer to this than I am in the biology world, that there may be a greater biomass beneath Earth's surface than above it.
I heard that too.
If you added it up, do you, this is something you remember from biology literature?
I remember hearing about that.
Yeah,
yes.
I just heard about it, right? But if that's true, that's just amazing, right? It meant here we are thinking how important the surface is and sunlight and this and that, and it's like, no, most organisms don't give a rat's ass about the surface. And exactly. But what that also means is judging whether Mars has life should not be a conversation about how hostile the surface is to life. And tell me, I'm going to slip this in. Matt, do I have permission to put in a question?
Granted.
Okay, thank you. We learn that ultraviolet light, which is not shielded on Mars from the sun, is hostile to biology. What is going on there? What is it? What is the ultraviolet? Why is it hostile to anything at all if it's just light?
Well, it's hostile here on Earth. I mean, the ultraviolet light is what causes skin cancer. And so it's such high energy radiation that it actually can kick off electrons off of atoms. And so in our electromagnetic spectrum, our weakest energy is going to be radio and microwaves. Then you have infrared and then your visible region. And then directly on top of that, that's where your ultraviolet kicks in. And so your ultraviolet, your X-ray, your gamma rays, those three main categories are such high energy radiation that they can spit that electron off of the atom. And when that happens in our body, that's what causes skin cancer. And so we really need to wear a sunscreen because essentially we have sacrificial molecules that we put on top of our skin that die, they split, okay, their bonds split, and that's what protects us because those molecules die, and then the ultraviolet radiation essentially goes to those molecules.
I'd love that. So
you're
saying the sunscreen is your sacrificial shield.
Yep, 100%.
Okay, wow. I hadn't thought about it that way.
Oh, interesting.
Yeah.
That makes. I didn't realize. I thought it sort of just bounces it in some way. I didn't realize it kind of works almost like a bike helmet where it just breaks instead of your head.
It's sunscreen versus sunblock. And so sunscreen has molecules in there that essentially absorb the ultraviolet radiation. And when that happens, their bonds break. And now they're no longer active. They can no longer protect you. And so you only have X amount of molecules you put on your body. And so when you run out of those sacrificial molecules, now you're just exposed. You're just sitting there with the UV radiation hitting your skin.
Damn.
Yeah.
Wait, so my clothing would be a sunblock.
Correct. Yeah.
Right?
Physically, yeah, it's a physical blocker. And so the sun block is like a physical blocker. And so for those, you're using nanoparticles, and like zinc or something like that, titanium.
Interesting.
But wait a minute, Kate. Yes, we get it that UV causes skin cancer, but there are UV chambers in hospitals that sterilize surgical equipment. And we're not asking whether those microbes are getting skin cancer. So what else is the UV doing?
It's the same thing. It's splitting the molecules. And so if you have essentially bad molecules on, your scalpel or whatever it is they're going to use in the hospital, you're killing the bacteria. And you can actually use UV radiation to do that. When COVID-19 kind of came out, they weren't sure in the very beginning if UV was going to be strong enough. They did a lot of research and they found out that we could actually use UV radiation to kill the COVID-19 piece.
Got it.
And so
Okay.
that's kind of neat.
So there's the virus getting skin cancer. No, the virus, whatever its
That's
basic.
a good way to think about it, though. I never
Right.
thought
Whichever
of it like
the
that.
basic molecular structure of the virus is, the UV is busting it open. Okay, that's very good
The
to know.
important part, not every bond, I don't want to imply every bond, but the important parts that make it dangerous, it breaks those bonds to basically make that virus no longer active. And so that's what sterilizes.
Very good. Very good. Okay, thank you. I slipped my question in that I'm not even a Patreon member. How do you like that?
I know.
Yeah,
Shameful.
Shameful. Okay.
The real patrons are going to be furious that
Okay.
an interluder is sneaking in.
Yeah.
Therese Talbot from Columbia, South Carolina says, are there any places in space where we cannot go due to reactions between a rocket's exhaust and potentially volatile chemicals in surrounding space?
I would say tentatively no, because usually space is the absence of molecules. And so I feel okay saying that there are protons moving around. I feel okay saying that there are some atoms in some areas. But in terms of having really big molecules that are going to have reactions, that's kind of limited. Now, all that being said, when we have, and Neil, you're going to have to fine tune this, but when we have supernovas that explode or they do their thing, then we can throw out those polyaromatic hydrocarbons. And those are out there, and we know that those can have reactivity. But in general, those are mostly stable.
So there's no need to strap a canary to the front of the rocket?
No, it would die for other
that.
reasons, I think. It would. It has to die for the reason you had in mind. So I'm just thinking, in the empty space, of course, Kate, that's right. There's nothing for your exhaust to interact with. So it'll just stay there as exhaust. But it had to take off from Earth's surface at some point, or at some other planet's surface that might have had an atmosphere. So we can ask, does it interact with Earth's atmosphere when it launches? And I can tell you that the main rockets, not the solid rocket boosters, but the main large engines are just hydrogen and oxygen in liquid state. And they're brought together with these valves. And Kate, tell us what happens when we combine hydrogen and oxygen.
we have a very beautiful combustion reaction. And so this is clean energy. And so hydrogen is an excellent source of fuel. It releases something like 286 kilojoules per mole of hydrogen. It's a beautiful source of fuel, and it doesn't have any carbon. Okay, so hydrogen by itself doesn't have carbon, so it doesn't release carbon dioxide, and that's why it's very clean and green, and we're not contributing to climate change.
Yeah, so the rockets that you see with all their plumes, the exhaust, most of that exhaust is just water vapor, I guess, right? I mean,
yeah,
that's
my understanding of it. Yeah.
Yeah, I don't want to go
vapor.
and breathe it like while that's happening because I think I would get cooked. But
right.
Right. There's no other chemical. No, there are different chemicals in the solid rocket boosters, but our mainstay throttleable engines are hydrogen and oxygen. And Kate, isn't that what they're talking about as another energy source for cars?
Oh yeah, absolutely.
How real is that? I mean, speaking as a chemist.
I am optimistic. I would love for that to happen. What I get nervous about is, in general, how would we do that? And so do you strap a hydrogen tank to the back of your car? So like the logistics of it makes me extraordinarily nervous.
And these are called fuel cells, I guess, right? That the fuel cell.
Well, yeah. You would likely use a fuel cell in this. And so you would need some kind of way to constantly input hydrogen. So a fuel cell is a cell or a battery, depending on how you want to talk about it, where you're constantly introducing your source of fuel. And so you would need a source of hydrogen. What I would love to see is if we would find a way to kind of do that safely so that we could burn hydrogen on our cars without producing carbon dioxide. To me, though, from my understanding of it, that just seems like a logistical nightmare.
So let me remind people that the Hindenburg was kept afloat by hydrogen. Okay. So if you have a tank of hydrogen, well, maybe it's not worse than a tank of gasoline. I mean, I don't know. We'd have to
No
ask.
spoilers, but how did it go?
Oh, for the Hindenburg? Yeah, no.
Yeah.
Yeah, that didn't end well for the Hindenburg. Matt, so let's see if we can slip one more question in before we take a break.
Okay, I'm gonna be cheeky and combine two questions because they're both about iron. Thomas Cochran, who's also a hematologist, so really into iron. I'm very happy to see Kate the Chemist returning. Says, I think iron is pretty neat. I also learned iron is responsible for the deaths of the largest stars in the universe. What is the unique chemical characterization of iron that makes it consume energy when it undergoes fusion or fission? And then Fadi Hayek says, we learn from Neil that the fusion process when stars form ends with a thud in iron. So how come there are heavier elements on Earth? Where did they come from?
I
think those are two questions that I think are playing in the same pool.
In it. Well,
yeah.
Okay, we don't have time to answer that in this segment. We can put a pin in that, and when we come back, more Cosmic Queries, the Chemicals Edition, Kate the Chemist. Be right back. We're back. StarTalk Cosmic Queries, Chemicals Edition with Kate the Chemist, who is an associate professor of chemistry and science instruction at UT Austin. And Kate, you now host a podcast that is about to drop that's sponsored by NPR, National Public Radio. So what's that about?
I'm so excited to announce this. It's called Seeking a Scientist. The first episode drops in April, and it's basically my dream job. I get to interview scientists doing cool science and highlight their amazing research. And we're really focusing on unique things that you might not know that much about. And so, of course, we're going to tackle the fungus zombies. We've got to talk about that. There's some new research out where you can reverse aging. So you can actually reset a heart by 10 years. So we're talking to scientists doing that. So it's just absolutely fascinating research. And my goal is to just turn scientists into rock stars.
Excellent. Especially if the science they're doing directly affects people's lives. Oh my gosh, all of a sudden people will start caring about them in ways they never thought that any of us thought was possible. So congratulations on that. We look forward. Maybe you can come back and tell us, we'll totally get you back to talk about some of who you interview. And Matt,
I'm gonna hold you to that. Let's do it.
Totally. and Matt, you're still hosting Probably Science, correct?
I am, yeah. So that's still going on. I love it when we found a bunch of listeners thanks to you and your show. So hi, fellow mutual listeners. And then
I was a guest on. Was it 30 years ago? I was a guest on your show.
Open invitation anytime. No, I want to say before you
don't call, you don't write, you know.
Oh, the second you need a 0.01% bump in your book sales, we are here. We are.
So what goes on your show?
Well, normally we go through the week in science news with are the comedians. So we get comics on, we talk about what's been happening, we riff with them, and then every so often we do special episodes where we have real scientists on, or science writers and communicators, and we talk about them and their work. So
Okay, cool.
Neil was a very special episode.
All right. Well, thank you. Very sweet of you. All right. So we're getting back into that question you left off with. It was from a hematologist. How often do you get a conversation with a hematologist? I guess that's blood, right? And
iron specifically.
And iron, yeah, exactly. Iron specifically. And he was trying to get all up in the astrophysical situation for iron. And Kate, we know in astrophysics that the buck stops at iron. When you're fusing elements, it's exothermic until iron, and afterwards it's endothermic. And then when you're fissioning elements, it's exothermic down to iron, and you try to fizz iron, then it's endothermic. So what's going on with iron that chemically in the nucleus?
And follow up from Fadi, how do we get things that aren't iron as well on Earth?
Okay, so my understanding of the iron component is, like you said, it's an energy piece. It's not necessarily specifically iron or the fact that it has, X, Y, or Z, but it has to do with the nuclear binding energy. And so binding energy, depending on what type of scientist you talk to, you're going to get a different definition. But in my world, what it means is how tightly those protons and neutrons and electrons are held into that atom. So how easily can you split that atom apart into its components? And so iron has a really high binding energy. And so those protons, electrons, neutrons are really held into that atom. Nickel is right next door to it. And so my understanding of this is that you can actually generate some nickel, but then it radioactively decays back to iron. And so in general, when we get to iron, it's like we've run out of fuel. And so hydrogen you can use, helium you can use, carbon you can use, oxygen, silicon, all of these you can use, and you can generate more fuel for the sun. I'll just call the sun. You can generate more fuel, and so it can keep doing its thing. But once you hit iron, now you cannot change the atom structure as easily. You cannot force iron to turn into another atom as easily because it takes too much energy. And so essentially it starts to implode, and then you kind of just crash out.
So, but in a supernova explosion, there's so much energy available that it doesn't matter that you're endothermic. You can absorb energy, and there's still plenty of energy around. So we can visit the heavier elements in the periodic table, but only when you have so much excess energy that it didn't matter that you ate some of it. And so, yeah, that's how you get right on up to uranium. Yeah, we're good there.
So I'm going to combine Biren Amin, Biren Brat, and Bjorn Furuknap, I hope I pronounced that correctly, because they've all asked questions about, is there a limit to the amount of elements that can be in the periodic table, how you go about updating it, whether you can discover new ones out there, and Bjorn wants to know whether there is a maximum possible size, whether you could even have an element that is the size, Bjorn says, of a Toyota Corolla.
Oh, I love that. Yeah, so Kate, where does it end? We're up to, what, 118 now, you said at the beginning?
Yeah, we have 118 elements right now on the periodic table. There's one professor who's been really driving the new formation of new elements. They're extraordinarily unstable. Like, they exist for less than a second. So it's unbelievably hard to characterize them and prove that you've made this element. You need high-tech equipment, you need all these things, and so it's very difficult for other places to replicate it. So right now, currently in 2023, I would say that the most possible chance of us having new elements would be because of Oganessian in California, because he just keeps sending neutrons at different elements in different conditions to see what he can come up with, and it's absolutely fascinating research.
So I read that if you go a little heavier, maybe into the 120s, 120 number of protons, that we might have an island of stability. How real is that? Or is that just Oz off in the distance? And maybe it's not real, we just wish it were real, where the element will last longer than a zillionth of a second?
I don't know. It really is going to depend on how many protons are going to be in the core, and more importantly, where the electrons are sitting in the outer shell. So I don't know.
But you've heard about this, right? I mean, so you're
have,
skeptical,
yeah.
you're saying. Is that?
I am. And it's just because our current research doesn't support that like at all. And so I understand why there's
Bummer.
thought about that. And the position in the periodic table would absolutely affect that. So I do understand that. That seems so far-fetched for me that it's one step outside of it for my personal comfort.
I wanted a fistful of element 125, whatever that would be, and walk around.
Me too. Someday.
All right, Matt, keep it coming. How many can we fit in?
Okay. Tom B. Knight, who's also a science fiction writer, wants to know what is the most powerful chemical explosive, and is it possible we would discover something more powerful? What elements or compounds would you start with if doing this research? And that feels like both a sci-fi writer's question and also something every kid in chemistry class wanted to know on the first lesson.
I never
what will
thought to
kill
ask
you?
that.
What makes the biggest bangs?
Cool. All right, Kate, what is it?
Oh, hysterical. I get asked that question all the time. So that's very funny. So we don't necessarily have like one that's the most explosive molecule here on Earth right now. But in general, what I can tell you about these molecules is they typically have nitrogen in them. Not nitrogen with triple bonds bound to each other, but there are nitrogen placed across the molecule. A lot of times it's like in a nitrate form, and so those are usually what is quite explosive. And
interesting. So the N in TNT comes from
Yes.
nitrogen, I guess, right?
Yes, it does. Yep, exactly.
Wow.
Yep.
Because today, when we measure the strength of nuclear blasts, it's in units of TNT. So that kind of feels like we're maxing out on sticks of dynamite. Or if dynamite's, I don't think, not technically the same as TNT. At least
Right.
slightly different, I heard. Is that right?
It's the composition, because dynamite has other stuff in there to try to keep it stable until you want it to react, right? And so there's that. So you're not just like walking around with actual trinitrotoluene. That would be incredibly dangerous.
Okay,
so you need something to kind of stabilize
If you're going to walk around with something, you want to walk around with dynamite instead of TNT.
I mean, I guess I wouldn't do either, but go ahead.
Oh, yeah. And Matt, that explains why the coyote always blows up, because
Yes.
it's TNT instead of dynamite. I remember that now. He should have spoke to Kate the
Foolish
Chemist.
coyote.
Foolish.
Man.
Didn't study enough. All right. Well, I love combining questions because James Hall from Texas says, I'm wondering about chemistry signs of extraterrestrial life. Are we able to see enough chemistry in exoplanet atmospheres to ask if they have similar pollution from burning fossil fuels, for example, CFCs? And then this is why I asked that one first before I move on to Richard Hart's question from Richard's 9-year-old daughter, Kyrene, who says, what kind of chemistry is happening in your body to cause you to toot? She wants to know if tooting is just you tooting at bacteria toots. I'm curious if these, quote, bacteria toots, as she calls them, are what scientists are looking for in the search for life on other worlds.
Oh, my gosh. Oh, my gosh. Kate, there you go. It's in your lap now. I'll defer to Kate on this one.
Okay. All right. Okay. So let's start with the extraterrestrial part. So the question was, would we predict the same pollutants in other areas? My response would be, it depends on the atmosphere of that planet. And so here on Earth, we have oxygen. And so when we burn fossil fuels, we form carbon dioxide. And that's what's causing climate change. And so if these other planets had oxygen in their environment, then yes, I would predict that CO2 would be formed if they burned something that's a hydrocarbon. I also want to fact check what was just said. CFCs are not generated in a typical combustion reaction. Yes, they contribute to climate change. They are a greenhouse gas, but it's not necessarily a byproduct of combustion.
CFC, chlorofluorocarbons, right.
Chlorofluorocarbons. Yeah, those are the ones that were banned back in the 80s when the ozone hole was getting really big. And a big piece of it is because they have a global warming potential of about 8,000. I think the number is like 8,100, whereas carbon dioxide has a global warming potential of 1. And we're terrified of what carbon dioxide is doing, and that has a level of 1. CFCs have 8,100, so it's pretty extreme.
Okay. And then, and how about tooting?
Tooting. Okay, so that has to do with what's in your body. And so essentially what you eat is then broken down. In our stomach, we have a bunch of different versions of acid. It's essentially hydrochloric acid and some kind of derivatives of it. And so the acid goes in. Your acid likes to donate a proton. And so it's going to react with what other molecules are that you just ate, and you're breaking down those species and then tooting them out. And so your toots could be composed of a number of different things based on what you've digested. So could we find life on another planet based on farts? I'm going with yes. If you somehow have a bucket of farts, then yeah, we could probably figure that out.
But the real question is, and I'm sure Matt is thinking this, he just doesn't want to ask it. Are toots flammable?
Absolutely.
This is the old camp question, okay?
Yeah.
When you go to camp,
do we need to be careful about rocket exhaust in the vicinity of a gaseous person?
Yes. I guess.
Yes.
So what is it that's in the tooth that's flammable? What chemical?
The two main primary ones would be methane. And so we know that from cows. When cows are eating their foods, they're pushing out a lot of methane. So they're
I know
contributing
methane
to
because that comes out of my stove. That's my cooking gas. Okay, and what else?
So that's CH4, and so that's extremely flammable. And then another part of it, and it's a very small portion of it, is hydrogen sulfide, and that's quite flammable as well. The sulfur typically has a rotten egg smell, and so if your farts ever smell egg-ish, there's likely a sulfur somewhere in your farts. I've never talked about farts as much.
Does methane itself have a smell? Because if it doesn't, then everything we attribute to the smell of fart would be the hydrogen sulfide. Is that right?
Yes. I mean, methane is definitely odorless. There's no color or anything like that. So I would say I feel comfortable telling you that methane, you're not going to smell it, but you're pushing out a lot of things. And so it's not just 100% sulfur.
Okay. All right. I don't know that we can follow that with another question. Okay. Let's leave that one exactly where it is. And thank Kate. Oh my gosh. Thank you for this. And like I said, we don't do enough chemistry on this program, and chemistry is everywhere at all times. And you're Kate the Chemist. So I don't want to pass up any possible future opportunities to bring you back. And so when you're deep embedded in your new podcast, we'll give you another call. We'll come back and talk about how that's going, and maybe tell us about some of your favorite guests that you've had.
Well, I've already learned you can't pick favorites, so they're all my favorite. Every scientist is my favorite.
We'll pick a favorite. That's right.
That's fair. I'll let you do that.
All right. And Matt, always good to have you there as my co-host.
Oh, so good. And thank you to the Patreon patrons. And there were so many great questions we didn't get a chance to get to. So you're going to have more chemists and more of Kate on soon.
Yeah, definitely. We won't miss out on that opportunity. This has been StarTalk, Cosmic Queries, the Chemicals Edition. I'm Neil deGrasse Tyson here, your personal astrophysicist. As always, I bid you to keep looking up.